Hello, and welcome to my talk on the label-free detection of dopamine using Aptamer-enhanced organic-electrolyte field effect transistor sensors. My name is Rosalind Massey. I'm a Master's of Applied Science student at Queen's University, and I'm presenting on behalf of myself and my supervisors, Professor Ravi Prakash and Professor Evelyn Moran. There is a large need for low-cost biosample quantification devices, and the OEGFET, or Organic Field Effect Transistor technology, provides a very interesting platform for this technology, because they are carbon-based thin-film transistors, which means that they can be printed at low cost and on flexible substrates, and they're also been demonstrated useful for sensory applications, with previous sensors being fabricated using OEGFET technology. Unfortunately, these devices often have low charge mobility, short shelf life, and poor gate insulation, which can lead to unpredictable operation. Our platform is either going to have to solve or work around these challenges. We have elected to use a form of an OEGFET technology called an Organic-Electrolyte gated field effect technology, transistor, which uses electrolyte as part of the gate dielectric. This gate can then be further functionalized using aptamers or enzymes to produce a transistor which has high sensitivity and high specificity for a certain biomolecule. We chose to functionalize our gate with aptamers, which are short DNA recognition molecules, which are proven to be thermally stable and environmentally stable, and can be immobilized on a gate with a very simple process. We had a aptamer designed for us by Dr. De Rosa of the Ladder Group at Carleton University, which had an incredibly low dissociation constant, which indicates that our aptamer has a very high affinity for our biomolecule of which we selected, which was dopamine. We selected dopamine because not only is it a physiologically relevant sensing target used in the diagnosis of Parkinson's and depression-related illnesses, but it is present in saliva, which is a biofluid we're interested in sampling, and it is comparable in both size and morphology to other relevant sensing targets such as cortisol. This is a basic example of an organic electrolyte gated field effect transistor device under no gate or channel bias. In this system, we see that the aptamers ideally will not be interacting at all with the electrolyte in our system. If we were to turn this device on, we see an electric double layer begins to form at the interface of the solid and the electrolyte. This is called an electric double layer, and this is actually what produces the sensing mechanism in the electrolyte-gated field effect transistors. In these systems, there is a change in transistor conductance, which is based on the change in the capacitance. In a system such as this, it is actually the electric double layer which dominates the total capacitive effect. So if we were to switch out this buffer solution with one containing dopamine, we see an interaction between the dopamine and the aptamers. These create a dopamine-aptamer complex, which actually takes over from the electrolyte double layer and kind of becomes the main effect in this system. And it produces a quantifiable and predictable change in transconductance, which we can leverage to quantify the amount of dopamine in solution. This is what makes these field effect transistors truly label-free, because we are seeing an actual change in the amperometric response based on the binding of dopamine to the aptamers. If we were to then take this system and wash it with, say, ascorbic acid, or not only do we reduce the pH, which causes the aptamers and the dopamine to dissociate, and we see a return to the previous level of current output. And we also see that we have produced a reusable device, as we are able to wash with ascorbic acid and reuse these aptamers in another system. We implemented a two-surface design. Our bottom surface, we ended up creating a cluster design, which allowed us to address different transistors with different aspect ratios and channel widths successively, and then we deposited our dielectric stack. We ended up using 100 nanometers of Teflon. rather than using something like PMMA, because we found that the Teflon not only reduced bioabsorption to the system, but it also did not interact as much with the buffer, which meant that we had a more consistent electronic output from our system. The second image here is what we're currently working on. We're using a dielectric stack, including PMMA, and a nanocomposite barium strontium titanate soil gel, because we found that it increases the dielectric properties effectively. Our top gate we built in-house using a glass slide and a P.PSS and P.PSS graphene top conductive gate. We found that the bilayer actually had an additive effect in increasing conductivity. On top of this, we deposited 200 nanometers of PMMA, and this PMMA we UV activated and drop cast our aptamers on. This was an incredibly simple immobilization process, especially when compared to something like immobilizing with an enzyme, which requires multiple steps and highly involved fabrication process. So this is the assembly that we ended up with 1 microliter of solution. We did a side-by-side test using a reference well and one with the aptamers, so we could collect concurrent characteristic curves. So our testing setup, as you can see here, is we did some static testing with a semiconductor parameter analyzer, and we had a constant gate bias of -1 volt, and we swept the channel bias from -2 to 10 volts. We wanted to have low power transistors, and as you can see here, by keeping them in this range, we are experiencing that. We found that there was probably an optimal channel bias of between 6 and 8 volts. We also did some dynamic testing with a high frequency pulse generator, and we used a pulse frequency in the ranges of 1 to 10 kilohertz. And we saw that our transistors had a response time of approximately 1 millisecond. These are some of the electrical output characteristic curves that we found for the current versus channel bias. As we can see, the one on the left is the reference, the one on the right is the sensing well. You can see immediately that there has been a significant change in transconductance for all of the systems that we tested. So we had 2 different dopamine concentrations, a high dopamine concentration of 1 micromolar, 1 micromolar, and a dopamine concentration of 0.01 micromolar, ascorbic acid and DI, and water as a control. I just want to emphasize this is the slopes, the linear range which we will be using for our testing for the high concentration dopamine. We can see that not only is there a higher maximum current output for the sensing well, we also see that it has a much longer linear range. This will give us more range for our sensors in the end. This is for the lower concentration. We see there has been a change in the slope, which indicates a change in transconductance, and again, differences in the current that we're finding for the system. Another important key fact that we noticed is we had an almost 3-volt change in turn-on voltage when we had the immobilized aptamers. This means that there is actually a reduction in power requirement with the aptamers immobilized on the gate. This is some of the parameters that we extracted from these values. I just want to point out that the orange columns have used a different aspect ratio, which is why they have slightly different values. But one of the interesting things that we noticed is the device transconductance parameter K prime P, which is the channel mobility multiplied by the capacitance, actually drops for the it's reference to sensing wells, which is surprising because we saw an increase in the channel characteristics, and so we expected to see this increase. We did, however, see an increase in the channel transconductance, which is reflective of the fact that we had higher channel currents for the same channel biases. We were able to demonstrate an organic-electrolyte gated field effect transistor with a detection time of approximately 1 millisecond. We had a limit of detection of 0.01 micromolar, which is in the physiologically relevant range. We were able to cover the entire thing with our 1 to 2 magnitude difference of concentration we tested. We're currently still working on testing the specificity of our transistor devices, However, we have done some testing with tyramine, which is a morphologically similar molecule, and we found that it does have a high affinity for only dopamine. Our future work, we're hoping to move into patterning this system on polymers. We've had some small success in this area, and we hope to expand on that in the future, as well as extending this to other physiologically relevant molecules. At the moment, we're working with cortisol to produce another OEGFET device for that. We're also looking at interfacing this system with a soft polymer channel pre-processing and sample intake system, and interfacing with some kind of CPU to create either a wearable device or some kind of point-of-care device. I'd like to thank everyone at the Organic Sensors and Devices group at Carleton University, with a special mention to Dr. Susie Baby and Mr. Alan Moore for their help with sample prep, at Queen's University Professor Evelyn Morin, and everyone at CMC Microsystems for their help with the fabrication process. This work was partly supported by the NSEC Discovery Grant and the CMC Assistance. Thank you. Does anyone have any questions?